In this video, I would like to show you how to use CellProfiler to analyze your images and a particular type of images, such as these. We have, let's say, a wide field image that shows the nuclei of a couple of cells, and we have in a second channel our infection marker. In this case, it's the influenza nucleoprotein that, in case of a positive infection, will render the nuclei green. So I want to show you how to use CellProfiler to count the number of positive nuclei from the total number of cells in the field of view. Okay, so let's say we have a bunch of images like these ones, different cell lines. We have one virus, we have different conditions, and we have different channels. So these are images that come straight from the microscope. So those you will need. The second thing you will need is that software CellProfiler. So you can go to cellprofiler.org and download it for your respective platform. So when you open it with my example pipeline, which is for the EVOS microscope, you end up with this type of window here. And the first thing we need to do is to import our images. So you can just drag the entire folder into that window or select the images manually like this. I'm just going to do that. Okay, so they pop up in here. You can include a filter that says use only, let's say, image data, use only a certain file format, and so on. In this case, we want to exclude these overlay images that the microscope produces automatically. So we just want to use the DAPI and GFP channels. So we say that the file should end with either DAPI or GFP, and we apply that to our list. I already see now that for the first one, there's the second channel missing. Okay, so let's make it easier. So for each of these fields of view, we now have two channels. Okay, so the second part will be to extract the metadata from these images, which will be done in this module. So it can extract the metadata from the TIFF file. Some of the data is already saved in the file, such as the channel name or some other information. But the most important part will come from the file name, which is this part, and it's this regular expression. And that usually takes a bit of time to figure out this sequence here to extract the information from the file name. In my examples, I usually just copy and paste an example that I've done previously. So usually I start from the end. So I say the file name ends with .tiff, and then we have these different fields, and the fields always have the same pattern. And in this case, they are just divided by underscores. So we have the channel, we have the field of view, which is a number, we have the condition, which is any symbol. In this case, I actually used all the wildcards so they can have numbers and letters. We submit that and we update our list. And what we hope to see is that for each image, we get the respective metadata, so the cell type, the channel, the condition, and the field of view, which is what we need to do the analysis. Okay, so we go to the next section here, which is to assign a certain name to a given channel. So in this case, I say we want to assign these names to something that matches a rule, and that rule in this case is that the metadata does have a channel matching that says GFP, which will put all the GFP images that have the channel GFP here, the metadata, in this case it's nucleoprotein. And the same for the DAPI channel, which is the DNA. So then we have a bunch of DNA images and we have a bunch of NP images. And that's about it, actually. So that's all that CellProfiler needs. It has image pairs for each field of view, and it will process them one after the other. So then we go into the actual analysis pipeline. And I have constructed this based on what I usually do to analyze this type of images, and I will show you how this works. So we have a couple of modules that we can use. You can find these modules down here. There's a couple of things for file processing, image processing, and measurements, and then also data tools to output. You can feel free to explore these and change and add and remove. I just have a couple of those here that I find useful. And you can, and during the development of these pipelines, you typically use something that is called the test mode that allows you to run each module one after the other to see the result immediately and adjust if necessary, which is of course necessary in the beginning. Okay, so what we want to do is we want to segment the nuclei, right? The nuclei will become then an object, and we want to measure the intensity of the NP signal within these nuclei. So this sort of object identification is behind these identify object modules. I'm just gonna start all of these. So the primary object is usually the nucleus. So this is the first thing to do. To make it a bit easier for CellProfiler, we can I usually rescale the intensity because it's often either too dim or too bright or not homogeneous enough and so on. In this case, it's actually quite nice, so I actually don't change it, but I still leave that module inside so I can show you what it does. The output is always this type of image here. So we have the input, which is the DNA image, and we have the rescaled intensity, which is almost the same. It's just sort of stretched across the entire range of the intensity. Okay, so using that image, we can then go into the primary objects identification. And that also, like all of these object identification modules, they require some parameter tweaking. So I give you this pipeline with parameters that I find optimized, but if you adapt this pipeline for something else, you might have to go through these parameters again. So things that are important are the size of the object, obviously, the input image, which is the rescaled intensity from the first module. The thresholding strategy is important. That also just, I usually trial and error. I just try a couple of things. For the nucleus, it's usually quite straightforward. So we can use OTSU for two classes, like either it's a nucleus or it's not. Then the only thing that we would have to optimize are these thresholding factors, and something that also is I would advise you to play around is these clumping parameters, so to distinguish objects that are clumped together. So I can show you what happens if I identify the primary objects from that first rescaled image. So in the test mode, it only always takes the first image. You can select a next image set, so a next field of view, but it will always only process one at a time. That's why it's a stepwise test mode, which is very useful. So it shows us basically the input image and the extracted nuclei, which looks already quite nice. If we go to areas that are very loose, like here, it's quite easy for CellProfiler to identify the nuclei. You can already see here, this one is sort of clumped together, but they are still divided. Here they are not. And this is something that is really hard to avoid. So there are always areas which are not as well segmented as other areas. So that's really part of the segmentation. It's sort of a compromise that will always have some trouble in very dense areas. So there are other ways to segment nuclei, but we'll not go into that now. But overall, I think it does a pretty good job in segmenting these nuclei. You see that some of them are just, they're clumped together. And that's something that can be, you can try around or play around with these sort of options here to distinguish the clumping, but usually for, let's say, a large fraction of that image, it looks actually quite fine. Okay. So the next part would be to identify the secondary object, which in our case is the cytoplasm, or in most cases would be the cytoplasm. And for that, we don't have an actual marker, but we try, or in this case, I try to use the nucleoprotein signal, which comes out as a background in uninfected cells. I can show you. So this one also needs some rescaling. Always pops up in my secondary window. So to make this again a bit easier for CellProfiler, I also boost the intensity here. So this is the input image. You can see it's quite dark in the background, and then there's some sort of background inside cells like this one. And to make this a bit easier for CellProfiler, I just limit the histogram to this custom range here. So I cut off everything that's above 0.2 and I cut off everything that's below to sort of remove the lower part and boost the upper part. of course, with these parameters, the cells that are actually infected will be overexposed. Makes sense, right? So these are saturated. But that's something that seems to work. So we use that rescaled intensity of the nucleoprotein, which I call rescaled NP, to identify the secondary objects. Now for the secondary objects, they usually start from the primary object to know where we would expect a cell. And then it uses some kind of method. You can try to understand how these methods work, but I think people spend quite a lot of time to optimize these methods. But it's worth to play around with these. In this case, I think propagation and minimum cross entropy thresholding works quite well. So these are sort of very advanced thresholding and segmentation routines that are used here. So let's do that for the nucleoprotein signal. So I already optimized these parameters and I played around with them, and when I tried it, I could not get it much better than what you can see here. But which for the cytoplasm, as I said, because we don't have an actual marker for the cytoplasm, is a lot harder than the nucleus. So let's look at some areas, for example, here where we have some cells that are clearly infected. So this cell is very easy. This cell looks quite nice. I think most of them still look quite nice. When the nuclear detection was sort of problematic, the cytoplasmic detection will also be. But in many cases, it looks actually quite okay again. So it's sort of a good compromise. You can look around a little bit here. It cuts off a little bit of the cytoplasm and so on. So with a dedicated cytoplasmic marker, this should be more straightforward. But in this case, we would anyway only use the nuclear object, but to have an example pipeline for cytoplasm and nucleus, I keep all of these things in. So having the cells and the nuclei, we can also then use this module identified tertiary object, which is just the difference between the two. So everything that is cell but not nucleus is then cytoplasm. That's how it looks like. So it's basically the cell with cut out nucleus. Okay, so then we are basically done with our object detection, and we can go straight to the measurement, which is down here. But to sort of keep track of these kind of processes, I in this case included a couple of overlays just for, as an output image to better follow how the processing works if you run this over a large number of images. So this is the first thing is to generate an overlay. This is quite straightforward. So it's just a nuclei in blue and infection signal in green. Now we can overlay the outlines that we have generated before on that image. That looks like this, and this is something that I think is useful to save in your output folder, for example. So to just know that the segmentation was sort of useful. In this case, it looks actually quite nice. So we have all the nuclei, they are detected quite well, and we have the cells that also seems reasonable. Of course, we don't see a lot of these cytoplasmic parts, but it looks, at first glance, looks reasonable. So that's something that I would suggest to export. So the next thing that I do before I save it, I make a tile image where the merged NP, the merged signal, and this overlay, this outline overlay, are sort of put together. And that's something that can be saved as an image, as a different module. I don't save all of the images, but just one. You can also select the number of cycles. So cycles like the fields of view that you process, you can select only the first, only the last, and so on. So I think one is enough, or maybe two, I think, to just follow to see if it is a useful segmentation. So then eventually we simply measure the object intensity. So For that we don't use the rescaled images, of course. So we want to use the raw images. We use the DNA and the NP images, and we measure all of these segments or all of these objects that we defined before. And that's it basically. So then CellProfiler will do this for all of the images that are in the folder, that are basically identified in the beginning. You can also have some options to display this kind of stuff, which is useful maybe for the test mode again. So let me show you. No, of course, the saving we don't do. Yeah, we can measure. So this little I here always stands for show me the output in a figure. So for measuring, it will just output this kind of table with some statistics. Yes, of course, we have to enable these before. So then we can display the data on image. That's actually not so useful, but you can also like display the NP intensity on the actual image. But what is maybe more useful is to look at the histogram, and also what we will do in the processing is to look at the scatter plot. So this is the histogram, let's say, of all the nuclei intensities that we found within this one image. It's just one image, a couple of hundred nuclei already. And the scatter plot is something that we will look at in the next video, which shows, in this case, the intensity of the DNA versus the intensity of the nuclei. And you can see, so this is an infected field of view, that we have a couple of negative nuclei down here. So the nuclei intensity sort of scales with this NP intensity. That's just size, I think. So it can be probably also normalized by the size, but we don't do that now. So we have these kind of negative nuclei, and we have a bunch of sort of infected cells. And the goal of the next part will be to extract the number of infected cells from that image. Okay, so now it does this analysis, and at the end what we want to do is we want to export this data, obviously, as a spreadsheet in this case. You can also choose database, I think, but spreadsheets are, I think, easy to work with. So we use a tab delimited file, which is just going to be a text file. We select an output folder. All sorts of naming conditions. And then something that is important to do is to select the measurement. If you don't do that, it will just export a huge amount of measurements, like area, we can look at it actually. So intensities, location, all sorts of things. It's really overwhelming almost. So in this case, I really reduced it to the minimum. What we need is the integrated intensity of that particular object. It also outputs all sorts of statistics already and so on. So, and we want to do that integrated intensity for all of the different objects, right? So for the nucleus, for the cytoplasm, and for the cells. I select data to export, so it will generate 3 independent spreadsheets for the nucleus, for the cells, and for the cytoplasm. So with that, basically, we have checked that our pipeline is working. It seems to be okay. So first of all, we exit the test mode. And then we don't want to see all of these images during the processing. I don't know how many fields of view I have in here, but we don't want to see like 100 images popping up, and it would also make the pipeline run slower. We don't need these display options also. The rest of them we can keep on. Okay, so with that we start our analysis by clicking Analyze Images. Yes, we can overwrite the existing files because I did this before to test it. So it found 44 test sets. Yes. Okay. So then it will show you the progress here. It takes a few minutes, maybe, depending on your computer and on the size of the dataset.